So for our next topic today, we have a barrel filled with a fluid to some height h, and this barrel has a length of L and a radius of R. And what we want to find today is we want to derive an expression for the pressure force that the fluid exerts on the sides of this barrel. So first we want to calculate the horizontal pressure force on one of the cylindrical halves of this. So I'm going to redraw this barrel from a side view. This will be the height of the fluid. So that's our h. And then of course it has some length L. And so we know that the force applied will be equal to the integral of the pressure times the differential area. And this comes from the pressure is equal to the force divided by the area. So because we are deriving this based on differential area, we need to split one of these two into either differential height or differential length. I will choose to do the height just because it works better for both iterations. So I'm going to change this a little bit. For pressure, I'm going to snub in rho g h. And for the differential area, I'm going to make that L dh, where that dh is some differential height there. And so as you can see, the differential area will be all these strips of dh multiplied by the length. So now we just need to pull out the constants. So we have rho g L integral from 0 to h of h dh. And so this will give us the resulting pressure force of rho g L h squared over 2. And so this expression shows the force on one cylindrical half of this barrel based on the length and the height of the fluid. So the next step is to find the force that's exerted on the circular end by the fluid. So to do this, I'm again going to draw a cross-sectional area of the view that we want. So as you can see, this is the end of the barrel with some radius r and height of the fluid h. So we're going to start like we did last time. The force is equal to the integral of the pressure times the differential area. And so first, I'm just going to say this pressure is equal to rho gh. However, it's not as simple as the last time. Because this is a circle, we would like to change all instances of h into polar coordinates. So we're going to change everything for h in terms of theta, which means, so because this height of the fluid is h, and we know the radius r, that means the distance from the center to the top of the fluid has to be h minus r. And then we can make this angle here some hypotenuse r, and we know that sine of theta is equal to h minus r over r, which is very helpful because it tells us that h minus r is equal to r sine theta. And because we know that h is equal to r plus h minus r, that gives us this function for h, which equals to r plus r sine theta. So now we can plug this in here. The pressure is equal to rho g times r plus r sine theta. And now we need to figure out what this differential area is going to be. So I'm going to make some differential height here. And notice I only went for half of the circle. So my differential area is automatically going to have a 2 in front of it because it's only half. So I'm going to say the length of that is going to be W. So the dA is going to be be 2w times the differential height dh. And again, we can use trig functions to find this w. So because we know this is r, then we know that w is equal to r cosine theta. So dA is equal to 2r cosine theta. And now dh, because we already derived this equation for h, all we need to do is take a derivative of it to find dh. So this gives us dh is equal to, derivative of r is 0 because it's with respect to theta. So all we're left with is r cosine theta because the derivative of sine is cosine. And then d theta at the end because we're deriving with respect to theta. So now we sub this in for the dh and we get r cosine theta d theta. Well, we can combine these to give us dA is equal to 2 r squared cosine squared theta d theta. Now we have to combine these to find the pressure, or to find the force function. So we have force is equal to the integral of rho g r plus r sine theta times 2r squared cosine squared theta d theta. So first we're going to take everything out of the integral that doesn't contain theta. So that gives us 2 rho g outside of the integral. And then I'm going to multiply these two together. So that gives us r cubed cosine squared theta plus r cubed sine theta cosine squared theta d theta. And from here, we can factor out an r cubed, which will also be a constant. So we can bring that out of the integral. 2r cubed rho g times the integral cosine squared theta plus sine theta cosine squared theta d theta. So this will be our function that we will use to find the force on the circular end of the. So now that we have this function for the force that the fluid exerts on the circular end of the barrel, we need to figure out our limits of integration. So our lower limit of integration is going to be theta 1. This is because this is where the height of the fluid is at its maximum. And our upper limit of integration is going to be where the height of the fluid is at its minimum, which is going to be negative pi over 2. And we know theta 1 from earlier, because sine of theta 1 is equal to h minus r over r. So we can rearrange this and state that theta 1 is equal to arc sine h minus r over r, which is simple enough. So now I want to separate these integrals into two integrals. Our first integral will be cosine squared theta d theta, and our second integral will be sine theta cosine squared theta d theta. And so these will be very difficult integrals to do by hand, but from Wolfram alpha, we know them very easily. So this first integral is going to be theta over 2 plus 1/2 sine theta cosine theta from theta 1 to negative pi over 2. And then it's going to be added to value of this integral, which is 1 over 3 cosine cubed theta. Theta 1 negative pi over 2. So now we need to figure out what the value of sine and cosine are at each of these points. So we know sine at negative pi over 2 is going to be equal to negative 1. We know that cosine at negative pi over 2 is going to be equal to 0. We know that sine of theta 1 is going to be equal to h minus r over r. That's because when you take the sine of an arcsine function, it will return whatever's inside the arcsine function. Cosine theta 1 is going to be a little bit more tricky. So using the identity function, or the identity property, we know that cosine theta is equal to the square root of 1 minus sine squared theta. And so substituting theta 1 in for this, we know that cosine theta 1 is equal to the square root of 1 minus h minus r squared over r squared. And so I want to FOIL this out, and I also want to get a common denominator for this 1 in this sine squared theta term. So the common denominator there would be r squared. So I'm going to have r squared minus h squared minus 2hr plus r squared all over r squared. So you see that r squared and that r squared cancel, which leaves us with cosine theta 1 is equal to the square root of 2hr minus h squared all over r. 2hr minus h squared over r. I'm going to go ahead and erase this because we're going to need some more room to write this answer. So now we just need to plug in those values and see what we get. So f is equal to 2 rho g r cubed. So the upper limit of integration be negative pi over 2. So theta over 2 is going to be negative pi over 4. And then plus, we know that cosine of negative pi over 2 is going to be 0. So this whole term is going to be 0. And then we're going to subtract. And we get theta over 2. So theta 1 over 2 is going to be 1 half h minus r over r. And then to that we add 1 half sine of theta 1 is going to be h minus r over r. And cosine of theta 1 is going to be the square root of 2hr minus h squared all over r. And then to this, we're going to add 1/3 of cosine cubed theta. Cosine cubed at negative pi over 2 is still going to be 0. And from that, we subtract cosine cubed at theta 1. So that's going to be this, or it's going to be 2 pi r minus h squared. That's going to be to the 3/2 power all over 3r cubed. So now this needs a little bit of simplifying, and we'll get our answer. We have f is equal to 2 rho g r cubed times negative pi over 4 minus 1 half h minus r over r minus h minus r times the square root of 2hr minus h squared all over 2r squared. We're going to combine all of those. And then minus 2 pi r minus h squared to the 3/2 power over 2r cubed. And this will be our final answer for the force exerted by the fluid on the circular end of this barrel. So as you can see, it's a very long answer, but it's all in only a few terms, and most of them are constants.